Then we're going to do exercise 5. I had some problems with the machine, so I have written almost everything already, so I will take you through the text. So I will try to do it slow enough. Exercise 5. Imagine all the families in the world with exactly 2 children. We allow ourselves the idealization that there is a 50-50 chance of having a girl each time you try, and we exclude families with twins. So, then we could first define G as girl and B as boy. Let's do that. And also let's define sample space of having 2 children. That sample space will be omega equal either you have 2 girls, or first one boy and second girl, or first girl, second boy, or 2 boys. So here we have the sample space. And we could of course calculate the probabilities of 2 girls. That should be the probability of girl and girl, which is the probability of girl times probability of girl, which is half times half, which is equal 1/4. And the probability of first boy and second girl, that is the probability of B and G, which is equal probability of B times probability of G, which is equal half times half equal 1/4. And in the same way, we will get probability for first child girl, second child boy 1/4, and probability for first boy and second boy 1/4. Then we can go to exercise 5a, where we are asked, among all these families with 2 children, one family is chosen at random, and you are told that this family has at least 1 girl. What is the probability that this family has 2 girls? So you are asked, what is the probability of 2 girls, given that this family have at least 1 girl? So what is the probability of 2 girls given at least 1 girl? This is nothing else but conditional probability. So we can write this as, remember, you can see it in the, see it here. Here we have conditional probability, where the formula is like this. So therefore I do the same here. And using base, we can go one step further and write this as the probability of 2 girls times the probability of at least 1 girl given 2 girls, divided of the probability of at least 1 girl. So just using conditional probability and base. And then I will use more notation, not just the words. So 2 girls would be GG, the probability of first girl and second child girl. And this one will be at least 1 girl, that is GG or GB or BG. Then we have at least 1 girl, given 2 girls, given GG. And this is divided on the probability of GG, at least 1 girl, which is GG or GB or BG. The problem is now finding these probabilities. The probability of GG, that's okay. The probability of GG, that's nothing else but 1/4. That we have calculated just in the top. Here you see probability of GG, that is 1/4. So that we can't miss. So this is actually 1/4. And this one, this denominator is equal the sum, that's the probability of GG plus probability of GB plus probability of BG, because the events GG, GB and BG are disjoint events. they don't overlap at all. So therefore we don't have to subtract anything, and we get 1/4 plus 1/4 plus 1/4, which is 3/4. So this one should be 3/4. Then we just have to understand this one. Here it says given 2 girls. What is then the chance of having 2 girls or 1 girl? That is, of course, totally sure. That's with probability 1. So this is 1. And the answer is therefore 1/4 divided on 3/4. And putting that in another way, 1/4 divided on 3/4, which is the same as 1/4 times 4/3, which is equal 1/3, which is the theoretical probability. And this is the theoretical probability that a family have 2 girls, given that they have at least 1 girl. And then we will do the same, actually, as we did in A, in B. Not exactly the same, because in A, we have all the families in all the world. We have the reality, but in B, we are asked to simulate this probability. And we can simulate this by the code given in the text. So we are just asked to understand the code in the text. And first of all, we import this NumPy package so we can do a lot of things with numbers. And then we set n equal 10,000. So we are going to simulate something 10,000. So the first we are doing here is simulate or drawing 10,000 childs called first child of the family. And we let girl b equal 1 and gives this a probability of a half. And let boy be 0 and give this a probability of a half. This is showed in this first line here. The range 0 and 1, we can have either 0 or 1 when we are drawing from this this random choice function. And as I said, 1 is now, we are calling that for girl, and 0 for boy. And here we see the probabilities for respectively boy and girl. And then we draw n times 10,000. Times from this so we randomly we draw 0 or 1 10,000 times, both with probability half. And then we simulate the second born, where we draw a new 10,000 childs, which are girls or boys, with both probabilities a half for being chosen every time. So this is just exactly the same as for firstborn. And then we initialize a variable who says how many families with at least 1 girl. And we set it to null, to 0 in the first, but this will change when we are simulating after on. Or going through the for loop below here. And we also initialize a variable who says how many families with 2 girls. And put this to 0 in the start. So, going through a for loop for n equal 10,000 times, and we're doing that to count up how many families having at least 1 girl and how many families having 2 girls. So, first we go into the for loop, then I is equal 0. Then we look at the first element in the first child array, which actually have 10,000 elements, but we're now looking at the first one, firstborn 0, and check if it's equal 1. If this first element is 1, or the secondborn array has first element equal 1, said in another way, it's a girl, then we let at least one go up with 1. So if the firstborn is a girl or the secondborn is a girl, we let at least one go up with 1. And then we also, in the same for loop, check if both childs, the first child and second child, are girls, and if both are girls, we let also the 2 girls go up with 1. And then we let the I increase to 1. So that's the second time we go into the for loop, and we are this time checking the second element in the firstborn array and check if that's a girl. And the same for the secondborn array. We check if the second element in that one is a girl, and if either one of them is a girl, then at least one go up with 1. And we do the same, and we also check the same element, element 2, in both firstborn and secondborn, and if both are 1, we let 2 girls go up with 1. So in the end of the for loop, we know how many families having 2 girls and how many families having 1 girl, and you could actually print 2 girls and print at least 1 to see exactly how many. And since then we just, and this last line here, print 2 girls divided on float at least 1, this gives the simulated probability for having 2 girls, giving that you have at least 1 girl. And this should be close to 1/3, because the theoretical counterpart is 1/3. So if we are drawing from the same world as the theoretical probability is calculated on, we should be hopefully close to this 1/3 of the real world. So let's do it and check if it's true. And we get 0.337, and that's pretty close to 1/3, 0.33333. Remark, this float command is necessarily tried without. Then we are going to exercise C, 5C, and that is actually exact the same way of thinking, but because of a lot more notation and more events, it gets harder. But let's try. So in the exercise, we are asked to know among all these families with 2 children, 1 family is chosen at random. And you are told that this family has at least 1 girl born on a Tuesday. What is the probability that this family has 2 girls? So the point here is that we are asked, what is the probability of 2 girls given at least 1 girl born on Tuesday? And now we do exactly the same as we did in A. We recognize this as a conditional probability and uses the formula for that and base. And then we get this first one to be equal the probability of 2 girls and at least 1 girl born on Tuesday divided at the probability at least 1 girl born on Tuesday. And then we can rewrite this one as the probability of 2 girls times the probability at least 1 girl born Tuesday given 2 girls divided on probability at least 1 girl born on Tuesday with use of base. But now the problem is, and instead of using these words, I will try to use more notation. And to do that, I let GT be girl born on Tuesday. I let G not T be girl not born Tuesday. And G is girl and B is boy. So instead of writing two girls here, then I can write probably of girl, girl. That's the same as two girls. And if I take this red one first now, how can we write at least one girl born on Tuesday? At least one girl born on Tuesday, that is first girl born on Tuesday and second girl not born on Tuesday. Or first girl not born Tuesday, but the second girl born Tuesday. Or the first girl born on Tuesday, but the second is a boy. Or the first is a boy and the second is a girl born on Tuesday. Or the first is a girl born Tuesday and the second is a girl born Tuesday. So this is the probability, this is the events that gives at least one girl born on Tuesday. And then we can also look at the green one here, which is then almost the same. It is at least one girl born Tuesday. That's the same as in the red here. That is all these combinations. Given two girls, given GG. So then the problem is how to compute these three sizes, these three probabilities. This one, the green one, and the red one. And one which is easily calculated is the probability of GG. The probability of GG, that is 1/4. That's half times a half, which we did in A. That is 1/4. First girl and second girl. And then let's take the red one. The red one can we write as following. We can write this red one as, I will write it here. So this is just that's this one. So the point is that we are going to compute the probability of the red circle above here, probability of first girl Tuesday, second girl not Tuesday, union girl first girl not Tuesday, second girl born Tuesday, or GTB union B GT union GT GT. And since all these events are disjoint, they don't overlap, they have nothing common, we can split it into a sum of the probability of the first one, GT times GT not Tuesday, plus the second one, the firstborn, a girl not born on Tuesday, times the second girl born on Tuesday, plus GTB, plus and so on. And these we can calculate if we think for ourselves. What is the probability that the first is a girl born on Tuesday? That's 1/2 to be a girl, and you should be born on a Tuesday, then it has to be times 1/7. And then we shall have a girl which is not born on Tuesday. That is a half being a girl times 6 divided on 7 for not being born on Tuesday, given that you are a girl. And so we can go on. and you can look at it carefully. Let's take this one again. GT, that's a girl born Tuesday. That's half times 1/7 times being a boy, which is a half, plus being a boy is a half times being a girl born Sunday is a half times 1/7, plus being a girl born Tuesday times being girl born Tuesday is a half times 1/7 times half times 1/7. And then we just can calculate this, and we get 6 divided on 196, 6 divided on 196, plus 1 divided on 28, plus 1 divided on 28, plus 1 divided on 196. And if we expand these two to get the same here, 196, we get 6 plus 6 plus 7 plus 7 plus 1 divided on 196, and we get 27 divided on 196, which is this red, which is this one. So maybe not very easy, and at all, at all. And then this green one, because here we have given two girls. So let's visualize that. Girl 1 here, girl 2 here. Girl 1 can be born on Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, or Sunday. The second girl can also be born at Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, or Sunday. So given that we have two girls, so that is actually these 49 dots, 7 times 7. Because that's all the combination of how these two girls can be born. Given that, what is then the probability that at least one is born at Tuesday? And here we can see that this one, if you take this one, here is girl 1 born on Tuesday, but the second is Monday. But that's enough, because that is at least one. Here is both born on Sunday. That's obviously at least one. Here is one. Here's the first girl and not the second. Here's the first girl born on Tuesday and not the second, and so on. If I sometimes say Sunday instead of Tuesday, I mean Tuesday. And here, if you look at this one, here is the first girl born on Friday, but the second girl is on Tuesday. So if you count up all these marked dots, we get 13. So 13 of 49 is the probability of at least one girl born on Tuesday, given that you have two girls. And then it is then we can calculate this one. And that is just 1 times 13, which is 13. 4 times 49, which is 196, divided on 27, divided on 196, which is equal to 1327. And this is a theoretical probability of having two girls, given that you have at least one girl born on Tuesday. That's what. Here we started. So go through it again and ask if you don't understand. D. So then we could have, and that's Python. So then we go to Python, and again we get some code from the text, and we are just asked to interpret it. So this time we have n equal 10 to the power of 5. So we use 100,000. We simulate 100,000 families instead of just 10,000 like in B. So and then we first draw 100,000 randomly chosen firstborn and check if it's a boy or girl. So we let 0 be a boy and 1 be a girl. And here is the probabilities for every event. Half is for 0 and this half is for this one. And then we draw again 100,000, but now we still is at the first child, but in some sense, but we are checking if we want to know if it is born on Tuesday or not. So we let Tuesday be 1 and not born Tuesday is 0. So not born Tuesday is 0, then this probability should be 6 divided on 7, which it is. And 1 is the probability. 1 is being born at a Tuesday, and that is with 1/7. That happens with 1 divided on 7 probability. So then we do the same for the second child of all these 100,000 families. So we get a new array with 100,000 elements, which is either called G or 0 or 1, which is for us boy or girl. And also this Tuesday array, which is filled with 1,000 elements of 0 ones, but now the zeros is not Tuesday and 1 is Tuesday. And then we initialize at a variable who says how many families with at least 1 girl born Tuesday. So this is our mark. You can't just use your interpretation from A directly into C to D here. No, your interpretation from B directly into D, because it's a slightly different problem. So be careful when you interpret it. So, and then we initialize 2 girls, which is a variable who says how many families with 2 girls and where at least 1 is born on a Tuesday. So then we're going through a for loop 100,000 times to count up how many families having at least 1 girl born Tuesday and how many families falling into the variable 2 girls. So if so we let first I be equal 0 and then go into the first element of first and choose 1. And if both have 1 inside, with both elements is 1, then we have a girl here and born Tuesday here, and to be girl and born Tuesday, this times this must be 1, because this is 1 if the first child is a girl, and this is 1 if the first child is born Tuesday. But also, or the second child is girl and born Tuesday. So if one of these are true, at least one goes up with 1. So the first line here, checking if first or second child is girl born Tuesday, and if either first or second or both child are girls born Tuesday, the variable at least 1 goes up 1. And here we are checking if first and second child both are girls. So first checking if both are girls, and if that's true, so we're checking if both childs are girl if at least one is born at Tuesday. What's written here? I think we write it down. Checking if first one is born Tuesday or second one. So if first and second are girls, and at least one of them born Tuesday, 2 girls goes up with 1. That was written here. So then we can calculate the probability. So this is just calculating probability of this one, 2 girls given at least 1 girl born on Tuesday. Then we can run it. And this should be very close to 13 divided on 27, which is a theoretical answer. And we get 0.479, and we then can check what is 13 divided on 27. That it's pretty close. we can see. And we could write this, take this again. And we won't get exact the same answer, but now we get 0.4828, and the first one 0.479 or something. And the truth is, as we just saw, 13 divided on 27. That's a theoretical answer. Just in between the two simulations. So then that was exercise 5. And then we're going to do exercise 6, but we can do that in the next video.